Hi, this is Kenny Lee, and let's talk about rotational dynamics. How do we explain when things are spinning? Right? Let's take a look at some of the basic kinematic type equations. Okay, so rotational dynamics. It may sound scary because now we're going to have everything spin, but really it's not that bad. If you look, a lot of times we're really going from like a Roman type alphabet to a Greek alphabet. So where we have velocity or speed equals distance divided by time, or displacement divided by time, in angular motion we'll have omega, which stands for angular speed, in radians per second, to equal the radians that it turned through in a certain amount of time. Again, acceleration, final velocity minus original velocity over time, angular acceleration, final angular velocity minus original angular velocity over time. They match up almost one-to-one. So it's the same style equations. It's just now we got to talk about things spinning rather than just moving at a constant rate across the ground or at some rate across the ground in a nice linear fashion. So let's take a look at a few basic problems here. But before we do that, go through a list. D, distance or displacement in meters. But theta is the rotational equivalent. That's your angular displacement or angle. That's in radians. A is for acceleration, meters per second squared. Alpha is for angular acceleration in radians per second squared. So basically we're changing the meters to radians. And of course T always stands for time. So let's take a look at one. A tire on a car rotates 15 times in 1 minute. What's the angular speed of the tire? Okay, now here's one thing. It doesn't give us the angle the tire went through. It told us that it rotates 15 times. So we actually need to figure out what theta is. Now, one time around is 2 pi radians. And it went around 15 times. So we just take 15 times 2 pi, and we get 30 pi radians is the angle that it turned through. That's one thing you have to look for to see if they gave you the angle or if they give you the number of rotations or revolutions in either case. So now we've got omega equals theta over time. And so theta is 30 pi. And you can leave it in terms of pi, but a lot of times we go ahead and multiply it through. And in 1 minute, so 1 minute is 60 seconds. So we can say that went through in 0.5 pi radians over seconds, or go ahead and multiply that through. So 3.14 times 0.5 gives me a velocity of 1.57 radians per second. As far as which one to use, it depends on what your problem looks like. Sometimes I want it in terms of pi, and sometimes they may not. So either way, all you have to do is just multiply by 3.14 or pi if you got that button on your calculator. Let's take a look at one where there's some acceleration going on. In a span of 2.5 seconds, a tire goes from 5 radians per second, in that case I wrote out the word, to 25 radians per second. What was its acceleration, angular acceleration, and what angle did it move through? So I'm looking for alpha, and I'm looking for theta. And I'm given a time of 2.5 seconds, an original speed of 5 radians per second, and a final angular speed of 25 radians per second. So let's take a look at this. First thing I want to do is probably find the acceleration, because I got a final velocity and original velocity. So I can do that. Alpha equals omega f minus omega o over t. So we've got 25 minus 5 over 2.5 seconds. So that means 20 divided by 2.5. We get 8. So the acceleration is 8 radians per second squared. So we got the acceleration. Now let's figure out the distance that it travels through. So that's theta. In this case, we're talking about distance as in angle. So theta equals omega OT plus 1/2 alpha t squared. I want to choose this one because I want to do these in a pairing together. I could actually use a different equation, but I'm going to go with this one for right now. So the original speed was 5 radians per second for 2.5 seconds. That's how much it would turn normally, plus 1/2 angular acceleration is 8 times 2.5 squared. So 2.5 squared times 4 plus 2.5 times 5 gives me 37.5 radians that it moved through. Easy enough. See, very similar to when we did kinematics. It's just now we're thinking about things spinning instead of things moving just along the ground. On this one, a wheel is rotating at 10 radians per second. A student's hand hits the wheel, so they're smacking the wheel to make it go faster, causing it to accelerate to 30 radians per second. If the wheel rotates 6 times during this acceleration, what's the wheel's acceleration? Okay, so it tells us how many times it rotated. So we actually need to figure out the angle. So we can take the 6 times it rotated times 2 pi, and we get that it actually went through 12 pi radians. Okay, keep that in mind. And now let's see, we've got the original speed of 10 radians per second. And the final is 30 radians per second. And we want to figure out the acceleration. Now, I don't know time, nor do I really care. It doesn't ask me for it. So in this case, I'm actually going to use this equation, omega f squared equals omega o squared plus 2 alpha theta. So final is 30 squared equals 10 squared plus 2. Alpha we don't know, but theta is 12 pi. And I'm actually going to multiply that out and get that into a number. So this will be 900 equals 100 plus 2 times 12 times 3.14, 75.36. 75.36 alpha. Then go ahead and work that math out. So 800 equals 75.36 alpha. And let's go ahead and divide. 800 divided by 75.36. And we get 10.62 radians per second squared. See, very similar problems to when we did linear kinematics. Tune in again, we'll talk about torque and moment of inertia. Matter of fact, we may do 2 separate videos on those. Thank you, and tune in again later. Goodbye.